So in this problem, the first thing I look at is this graph going to point up or down? The way I'm going to determine that is I'm going to look at the number in front of my x squared, my a value. If it is positive, this graph is going to go up. If it's negative, it's going to go down. This also is asking me to graph or to list the axis of symmetry, the vertex, and the y-intercept. And so I'm going to use these little shortcuts when it's in standard form. If it's in vertex form, then you kind of already have it. But if it's not in vertex form, if it's in standard form, then you have to actually calculate it. So if I look at this one, negative b, well, that is negative 4 over 2 times a, which is 2. That gives me a negative 4 over 4, which gives me negative 1. And so I have my axis of symmetry. My axis of symmetry here is negative 1. Your axis of symmetry is going to just be a dashed line. It's going to tell me where that graph is going to mirror across. So it's not actually part of my graph, but I'm going to graph it with a dashed line just to help me graph the actual function when I finish all of this. The next piece is the vertex. So the vertex, I've actually already found my x value. That is negative 1. To find my y value, I plug it into my function. So I have y equals 2x squared. Well, I'm going to plug in that negative 1. Plus 4. Again, plug in the negative 1. And minus 1. Negative 1 squared is 1 times 2. 4 times negative 1 is negative 4. And then minus 1. So I have 2 minus 4 minus 1. That gives me negative 3. So that tells me the y value of my vertex. So I know my vertex happens at negative 1, negative 3. That's the point right here. You just find it on your graph. And then my y-intercept when it's in this form is pretty easy. It's going to be 0 and my c value. My c value here is negative 1. And so I'm going to plot that point, 0, negative 1. Once I have a point off of the vertex, I can just mirror it. So I have this point right here. I can just say, well, it's 1 away from my axis. I go 1 away on the other side and put a point there. And then you can see how this is going to graph. Remember, parabolas are curved. They're not sharp points. Sharp points are absolute value. So I am going to curve this guy and graph it. So you'll notice this one has an equal sign. That's just the graph. If it had been a greater than or less than, I would have shaded either above or below the graph. So this is an inequality, but it's still a quadratic. It's also not in standard form, it's in vertex form. And so this is actually a little bit easier. My a value is still going to tell me if I'm going up or down. So in this case, my a value is negative. So this graph is only actually going to point down like that when I finally get done with it. That's what that tells me. My axis, I don't actually have to calculate. My axis is the h value. And if you recall, it's opposite of what you see. So it's always going to be the opposite of what you see inside of there. Technically, h is, in the formula, it's minus already. And so that's why you use the opposite of what you see. So in this case, I see a negative 1, but my axis is actually going to be x equals positive 1. So this is a, this is h, and this is k. My vertex is just my hk, all right? And so my h is 1, and then k, we do whatever it says. It's a positive 2, we leave it as a positive 2. So my vertex here is 1, 2. The only thing I have to actually calculate when it's in vertex form is the y-intercept. And I do that just by plugging in a 0. So my y-intercept is always going to be 0, and then what happens when I plug in a 0? So I'm going to say, well, let's plug in a 0. Negative 4, 0 minus 1 squared plus 2. And then we just do order of operations. 0 minus 1 is negative 1 squared plus 2. Negative 1 squared is 1 times negative 4 plus 2, negative 2. So my y-intercept here is going to be 0, negative 2. That's the only one you have to calculate when it is in vertex form. And I'm going to graph it the exact same way. I'm going to go to positive 1, which they did not give me. These are in sets of 2, so just pay attention to that. So I'm going to go to positive 1 and do my dashed line. I'm going to graph my vertex. My vertex is at 1, 2. 1, 2 is right there. I'm going to graph my y-intercept, which is at 0, negative 2, which is right here. And then I'm going to mirror that. So it's a half a block. It's just 1 unit away from my axis. So I'm going to go over here and mirror that right there. All right. Now for inequalities, I have to look at 2 things. Does it have the or equal to sign? That means it's going to be solid. If it was just a less than or just the greater than, I would make it dashed. But it is solid. So I'm going to graph this with a solid curve here. Okay. And then the next thing I'm going to look at is greater than or less than. Greater than means you're going to graph, so everything, when I do greater than, I look at my vertex and I say which side of the parabola shows greater than. Well, this side of the parabola would be greater than. Okay, so I'm going to actually shade everything on that side of the parabola. If it was less than, the inside of the parabola here would actually be less than. Now, if it were flipped up the other way, that's actually opposite. Greater than would be on the inside of it and less than would be on the outside of it. So you just have to look and see which way is it facing and which would make it follow those rules. So this one is actually going to shade everything on the outside. That is greater than. And technically it keeps going infinitely. All right, so remember with division, you can either do long division. Long division looks like this, just like it did when we were in elementary school. We do what we're dividing by on the outside and what we are dividing on the inside. Remember, if I start at x to the 5th, I need to have a 5, 4, 3, 2, 1, and a constant. So it's going to look just like this. We're just going to set it up. And we're going to do long division just like we would have done. All right, the other way to do it is synthetic. Synthetic just looks like it's upside down. Instead of writing my x's, I write just the coefficients. So I have a 1 in front of the x to the 5th, then a 6, then a 12, then a 1, then a negative 2, then a negative 2, right? And on the outside of synthetic, I use the opposite. So this is a positive 1. I'm going to use a negative 1. All right. And then we just add down, multiply up, if you'll recall that little method. So I'm going to add down 1 plus nothing. Well, that is 1. Then negative 1 times 1, that's negative 1. Add down, by the way. 6 plus negative 1 is 5. And then negative 1 times 5 is negative 5. And then I'm going to add down 12 and negative 5, 7. Multiply up, negative 7. 1 and negative 7, that's negative 6. Multiply up, 6. Negative 2 and 6 is 4. Multiply up, negative 4. Negative 2 and negative 4 are negative 6. All right. To finish it with synthetic, I'm going to put my variables back in. If I start at x to the 5th, my first one is going to be 1 down from there. So I have 1 x to the 4th plus 5 x cubed plus 7 x squared minus 6 x plus 4. And this last guy is my remainder. My remainder, I do 6 over what I was dividing by, which was x plus 1. And that is my answer. All right, when it says synthetic substitution, You actually do exactly the same thing. You make sure that you're not missing any pieces. I started at 4, 3, 2, 1, and a constant. You do not make it the opposite when it's synthetic substitution. They gave you what you are dividing by. You just use that positive 3. However, your answer is only the remainder. You do not have to fill the x's back in. Your whole answer is just the remainder, and not the remainder over what you were dividing by. Just the remainder is your answer, okay? It's basically telling you what would happen if you plugged a 3 in for all those x's. What answer would you get? It is the remainder. That is the answer you would get if you did that. And so you do it exactly the same. Add down, multiply up, all the way across, but then you're just going to circle that remainder, and that is your answer. In this problem, to factor completely, you're going to look at this 72, and you're going to say, what factors of 72 add up to give me 17? Well, that's just 8 and 9, right? And instead of to the 4th, we're just going to cut that in half. So like if it had been squared, you would say x and x. So when it's to the 4th, just say x squared, or in this case, u squared. So I'm going to say, well, u squared plus 9, u squared plus 8. That's it. That's all you do. All right. If you have a special case, like let's say this had been u to the 4th minus u squared minus 72. We'll do that. That would be u squared minus 9, u squared plus 8. All right. This is different than the one I just did because this is a special case. This is the difference of two squares. So I could keep going. And I could say, oh, well, I can factor this guy to u plus 3, u minus 3, and this one I have to leave alone. All right, so they're looking to make sure that you, 1, are factoring the first piece of it correctly, and 2, did you create a special case when you did that? You will only have special cases if it's subtraction with 2 perfect squares, okay? The u squared plus 9, you can't factor him anymore, all right? But you can factor u squared minus 9. That's the only time you can keep going if it's a perfect square and it's subtraction. Zeros. So zeros are when we set something equal to 0 and solve. There are certain zeros that pair up. All right. If you have imaginary zeros like 2i, that's an imaginary 0, then you have to assume negative 2i is also a 0. The other one is square roots. I is the square root of negative 1. So remember when we solve for roots, we do positive and negative root. If I were to say x squared equals 9, I would say, oh, positive and negative 3. So roots also have a pair because you know it had to come from a square. It had to come from square to get a square root. And so when it says find additional zeros, anytime I have an I, I'm going to have additional 0. It's the opposite. Or if I have a root, like this square root of 3, my additional 0 would be negative square root of 3. So that's the first piece. Do I have any additional zeros? If I have an I or a square root, the answer is going to be yes, and you need to tell me the opposite. Then it wants me to write the polynomial, okay? Writing the polynomial just means doing an x plus or minus the problem. So it's always the opposite. So I have a negative 3 here. It's always minus, so I'm going to say minus a negative is going to be a plus 3 for that one. I'm going to group the square root. That's a positive root, so I'm going to say x minus the square root of 3. And then I have this negative, so it's going to be plus, x plus the square root of 3. All right? That's how I set this guy up. And then they want me to actually FOIL it. A little tip, always FOIL your conjugates first. By conjugates, I mean if you have some number plus and some number minus the same 2, always do those first because they will always be the first one squared minus the second one squared. Just like factoring, we're now FOILing. We're going the other direction. So I'm going to do these groups first because they're easier. I'm going to leave the x plus 3 alone. And I'm going to say, well, these look just like this. It's the same two numbers, but it's a plus minus. So it's going to be the first guy squared. That's just x, right? X squared. Minus the second guy squared. What happens when I square a square root?
Just because of no number.
Right, so if I square the square root of 3, I'm just going to get 3 here. And so that one was much easier to do. Now, this last piece, I just FOIL. We've been foiling since Algebra 1. First, outer, inner, last. So I'm going to take the first one, x times x squared. That's x cubed. X times negative 3. Negative 3x. 3 times x squared plus 3x. And 3 times negative 3 minus 9. And that's a squared. I do want to put this in standard form. Standard forms means highest degree to lowest. So I'm going to say, well, x cubed, that's the highest. 3x squared, that's next. Negative 3x. And then negative 9. And that is the second piece of that. So I gave the extra 0 there. That answered that. And then write it in standard form here is that one. So a negative. So I'm going to write degree here so we have a little chart. We'll look at degree. If my degree is even, they're going to go the same direction. If it is odd, they're going to go different directions. All right. Now the next piece is, how do I know which direction they go? And for that, I am going to look at my leading coefficient. If my leading coefficient is positive, it goes up. Either both up or up from left to right. If it's negative, it goes down. Either both down or down from left to right. So I'm going to look at those two things. So for this one, I'm going to look at my degree. My degree is 5. 5 is odd. So it means that they're either going to go that direction or that direction. I know they're going to go opposite directions on the end when this graph is graphed. Right? Then I'm going to look at my leading coefficient. My leading coefficient is negative 1. It's the number in front, negative 1. Which means I just narrowed it down, right? Negative tells me it's going down. So my answer is, it goes up on the left and down on the right. So there's a couple ways you can write that. It'll say, in your answer key, it may say rises to the left, falls to the right. I will take a picture, if you want to draw it. I will take, it's up on the left, down on the right. That's acceptable. I'm sure nobody's going to do the last one, but we did talk about limit. As x is going to the left, which is negative, this is going up, and as x is going to the right, which is positive, this is going down. All right, chapter 7 was all about radicals. So simplifying radicals, adding and subtracting radicals, multiplying and dividing radicals, etc. And so first of all, you need to make sure you know how to simplify a radical. That is really just your factor tree. So I am going to just use my smallest one that I can. I know 2 goes into every even number. And then you're just going to factor all the way down. Oh, I wrote it. I'm doing it out. There we go. That's better. All right, and so you're just going to factor it. Easy enough. Then you're going to look at your index. My index here is 3. So everything that groups in 3s can come out. I also need to notice that I already have something on the outside. So I already start with a -3 on the outside. He's going to already be there. And then every group comes out as 1. So I have a group of 3 2s here. That's going to come out as 1 2. I have another group of 3 2s. That's going to come out as 1. And then little 7 here is all alone. He has to stay in. Don't forget to put your index back out there. And then just multiply. Whatever stays in multiplies, whatever comes out multiplies. So I have -3 times 2 times 2, that's -12, cubed root of 7. If I had variables involved, you can really do the same thing with the variables. Let's say you have x to the 4th. 2 ways to do this. You can divide, 4 divided by 3, or you can just say, well, that's 1, 2, 3, 4 x's. And then I'm going to group it in 3s, right? Just like my index. 1x will come out, 1x would stay in. So that's what this guy would look like if it was a variable. You literally do the same thing. Just draw one for each number that you have and circle it, right? If you remember the division, you can do that. 4 divided by 3 is 1 remainder of 1. That tells you what comes out, what stays in. Or you can simply draw it and circle it like you did with the factor tree. When you are adding, you have to have like terms, which means your index has to be the same and the number inside has to be the same. So if I look at number 27, it looks like nothing will add. But before I can make that decision, I have to actually simplify it. And so I'm going to do exactly what I did on the problem above it. I'm going to use my factor tree. 2 and 12, 2 and 6, 2 and 3. I already have a 3 on the outside. This is an index of 2, so there's a group of 2. 2 and 3 will stay in, so that is a 6. Do the same thing with the 20. 2 and 10, 2 and 5. All right. I already have a 3 on the outside. I have a pair of 2s that can come out. And I have a 5 that will stay in. I have a minus, and then I'm going to do the same thing here. 2 and 3. Nothing can come out, but I already have a 2 out here. Two and 3 stay in, so I have a 6. Simplify and then add and subtract. 3 times 2 is 6 squared is 6. Plus 6 squared of 5 minus 2 squared of 6. These are now like terms. 6 minus 2 is going to give me a 4. So I have 4 squared of 6. And then this cannot combine with anything. So plus 6 square root of 5. And I am done with that one. So I am going to look at my outside numbers, in this case a 1 up here and a 5. Can I reduce those? No. A 3 and a 5, can those reduce? No. If they could, I would reduce them just like I reduce fractions. The second thing I look for is, can the radical itself simplify? Like, had that been an 8, well, 2 times 2 times 2 is 8, so I would be able to take a 2 out, leave a 2 in, right? I could simplify the radical. So I'm going to go through those steps first. Can I reduce my fractions? Can I simplify my radicals? And then once I've done all of that, I need to get my radical out of the denominator. And so that is rationalizing my denominator. So I'm going to take that square root of 5 and I'm going to multiply the top and the bottom by the square root of 5. Remember, when you multiply radicals, you just multiply what's inside. So on the top, I have the square root of 3 times 5, which is the square root of 15. On the bottom, I have that 5 out there. And then when I multiply a radical by itself, it becomes just what's inside. So I have 5 times 5, which is 25, all right? You are going to be tempted to reduce this because you're going to look at 15 and 25 and say you can take something out. However, 15 is inside the radical, 25 is outside the radical. I cannot reduce those. That is my answer. So when you have something like this, we can't just multiply by one of them. It's going to cause a problem. So we're actually going to multiply by the conjugate. If you remember, the conjugate is the same two numbers, but just with changing the sign in between them. So I'm going to take this denominator and I'm going to multiply it by the square root of 5 minus the square root of 2. And since I'm multiplying the denominator by that, I have to also multiply the numerator by that. All right? In the numerator, I just distribute. 5 times this, well, it's outside and inside, so this 5 stays on the outside, and I have a square root of 5 on the inside. That is minus. And then I have 5 times the second piece. 5 on the outside, square root of 2 on the inside. That's all I do there. For the denominator, anytime you multiply conjugates, it will always be the first guy squared minus the second guy squared. All right, so it's always going to be this guy squared minus the second one squared. All right, and I am squaring a square root. So numerator stays exactly the same. Denominator, though, I'm squaring a square root, I get what is inside. I'm squaring a square root, I get what is inside. And then I can actually subtract there. So my final answer for this one is going to end up being 5 square root of 5 minus 5 square root of 2 over 3. I cannot simplify that anymore. I will just leave it. You do exactly the same thing if there's an I there. All right, so you are just going to multiply the top and bottom by the conjugate. Now, conjugates do not change the first one. So that's a -8. It's going to stay a -8. It just changes the second one. It was a minus. We're going to change it to a plus. All right. Numerator, we do exactly the same thing. Distribute. So I'm going to distribute the 2 through to both of those. 2 times -8. 2 times 9i. On the bottom, again, I'm multiplying conjugates. So I square the first one. -8 squared. It's always a minus. Square the second one. 9i squared. On the top, I can't simplify it anymore. That negative and 16 and the 18i can't simplify because of that I. It's in there. So I'm going to leave it a -16 plus an 18i. In the denominator, I can do the -8 squared. That is 64. 9i squared. Well, 9 squared is 81. And I have an I squared. If you will recall, I squared is -1. You just replace it with a -1. So I technically have 64 minus 81 times -1 right there. Well, so this is a negative and a negative, so I technically have 64 plus 81. All right, I will always change that. I squared will always change it. So my final answer for this one, my numerator hasn't changed. My denominator is going to be 64 plus 81, which is 145. If I could take something out of all three of them, I would reduce. Nothing goes into all three of those. So that is actually my final answer there. You may have ones that have a number on the outside, a variable on the outside, or they have radicals on both sides. Any of those can happen. And so to get rid of a radical, we need to make sure it's by itself first, and then we need to square both sides. So like on 39, the radical's by itself. I am going to square both sides. I'm going to square the 10. I'm going to square the radical. On the left-hand side, 10 squared is 100. On the right-hand side, when I square a square root, I have what is inside. So I have 34p minus 2. And then I have a pretty basic equation. I need to solve it by adding my 2 over. 102 equals 34p. And then I'm just going to divide by 34. So divide both sides by 34. 34 actually goes evenly into 102. And that is my answer. It says check for extraneous solutions, which means you need to plug it in and make sure it actually works and you didn't cause a problem in the root. But as long as you didn't cause a problem, you are good. All right, for this one, I actually have a radical, but they are technically by themselves on each side. So I'm going to square both sides. And both the radicals are going to go away. On the left-hand side, I just have n minus 7. On the right-hand side, I just have 15 minus n. In this case, I want all my variables to one side. So I'll add the n over here. And then I want my numbers on the other side. So I'll add my 7 to the other side. So n plus n will give me 2n. 15 plus 7 will give me 22. And then I'll finish it out by dividing. When you have something like addition, you're literally just combining like terms. So what this means is the f function, which is t cubed minus 2 times t, plus the g function, which is 3t plus 4. So you just combine like terms. Nothing combines with this. These two will combine, and this doesn't combine with anything. That is your answer, right? So for addition and subtraction, you're just combining like terms. Multiplication, you would FOIL. And division, you would just put the numerator in the top and the denominator in the bottom, right? So those operations are pretty simple. Composite, well, composite means to put one function inside of another. All right? So for this, they are asking for the composite of f of g, which means I'm going to take g and I'm going to put it inside of f. There are two ways to do a composite, okay? The first way is I actually take the entire g function and I plug it into f. So I have 4. Instead of n, I'm going to write g, n squared plus 4. And then I have plus 5. So this is my f function, 4n plus 5. I just replace the n with my g. All right? Distribute 4n squared plus 16 plus 5. And I have 4n squared plus 21. All right? That is just f of g. So if they just asked for f of g, we would do that. All right? They ask for f of g of 2. All right? So then there's another way to do this. You can first, if you find this, just plug in a 2. All right? So we can just say, well, I want to plug a 2 in here because that's what they're asking for. And I have 4 times 2 squared plus 21. We can do that, all right? 16 and 21, that'll give me 37, all right? Or you can take the 2 and plug it into the g, all right? So I can take it and plug it into my g function. So my g function at 2 would be 2 squared plus 4, right? Which is just 8. Then I'm going to take that answer, which was 8, and I'm going to plug that into f. So my f function, when I plug in an 8, is 4 times 8 plus 5. That's 32 plus 5, which is 37, which is the same answer when I did it that way. So when you have a number, you can do it two ways. You can plug the function in and then plug the number in, or you can plug the number into the function and that answer into the first function. Whichever way, you will get the same answer. First, remember that f of x just means y. All right, that's all that means. So my first step here is to switch x and y. And then you're going to solve for y. All right, so if I switch my x and y, I literally write an x every place I have a y. And I write a y everywhere I have an x. That's my first step. My second step is then to solve for y. So in this case, I would need to move my 3 over. So on the left-hand side, I have x minus 3. And on the right-hand side, I have negative 4 over y minus 1. All right. I will say when it looks like this, so my y is on the bottom, and that's what I'm solving for, you can just flip both sides, okay? So I don't have a denominator here on this left-hand side, so technically we don't have a denominator, it's a 1, right? Anytime what you're solving for, in this case y, is on bottom, you can literally just flip both sides. So flip both sides. So on the left, I have 1 over x minus 3. And on the right, I have y minus 1 over negative 4. It just helps to solve. And then I can say, okay, well, I'm still trying to get y by itself. Multiply both sides by negative 4. So on the left, I have negative 4 over x minus 3. And on the right, I have y minus 1. Still don't have y by itself. I have one more step. I need to add 1 to both sides. So on the left, I have negative 4 over x minus 3 plus 1 equals y. And so my final step, once I have solved for y, I'm going to rewrite it, the y, to be f prime of x. That tells me I found the inverse. And so instead of writing a y, just write f prime of x. So exponential form, to get this to exponential form, he's going to look like this guy. And this one to write in logarithm would look like him. So my base of my logarithm is always the base of my exponent. So 1/13 is going to be the base. And what it equals is my exponent. So I have a base to the second power. And then that will equal what I was taking the log of, 1 over 169. You can see if this is true. Does 1 over 13 equal 1 over 169 when you square it? Well, yes, 1 squared is 1, 13 squared is 169. So 1/13 squared is 1 over 169. Like, this should make logical sense when you rewrite it, okay? So then the second piece, the next one, is going to just rewrite it to look like the one above it. So now my base is still the base. So log, and my base now is 121. And that is, I am taking the log of now what would be my answer. So now I'm going to write 11. So basically I'm saying 121 to what power equals 11? Well, 11 is technically the square root of 121, and we write square roots like that. So that becomes what it equals. All right, so my bases are always my bases. This will now become what I'm taking the log of, and my exponent is my answer on a logarithm. So if I look at this first one, it is division. So I can break this up into multiple logs by subtracting. So I'm going to say log base 3 of my numerator, which is 10 cubed, minus log base 3 of my denominator, which is 7 squared. And then I can apply that third rule and move those exponents. Those exponents can go in front. So now I have 3 log base 3 of 10 minus 2 log base 3 of 7. That's all I'm doing here. I'm just expanding. All right, condensing. So this one just takes it from multiple logs, and your goal is to put it into one logarithm, all right? So the first thing I'm going to notice is that I have coefficients that could be exponents. All right, so this first one is easy. This is obviously my coefficient, 3 log base 5 of w. This second guy I'm going to rewrite before I condense, because when you have something over a number, it's like multiplying by that fraction. So something over 2 is the same thing as multiplying by 1/2. So I can just look at that as a 1/2 log base 5 of u. All right, so I didn't actually condense yet. I just rewrote that fraction. And now I'm going to condense them all into one. Anytime I'm condensing, I usually do my coefficients first. So remember, these can become my exponents. So I can put that as that guy's exponent. This one is that one. So I have log base 5 of w to the 3rd power plus log base 5 of u to the 1/2 power. All right. Then I'm going to look at the fact that I am adding. Remember, addition relates to multiplication. All right. So I can make them all one logarithm by multiplying them. So I'm going to keep it a log base 5, and I'm going to multiply these w to the 3rd times u to the 1/2. I will say one thing that you need to do is anything to the 1/2 power is the same thing as writing it as a square root. So the final rewrite here is to say, well, that's log base 5 of w to the 3rd, and this is actually a square root. So square root of u. My final answer should have only one logarithm in it. All right, there's two things you can do with solving. One, if you don't see any common base, you can just use logarithms. Take the log of both sides, right? And then expand. So what I mean by that is, I personally can see that this is the same base of 4. I can see 4 cubed is 64 and 4 squared is 16. And then I can solve it that way, all right? But let's say you don't notice that and you're like, what do I do? You can use logarithms to solve it as well. And so I can actually say, well, let's take the log of both sides. All right. So I have log 64 of x to the x minus 3 equals log of 16. All right. Well, I need that x. That's what I'm trying to solve for. And it is in my exponent place. So when I know expansion will let me move that in front. So I'm actually going to expand it and move this guy in front. Get him out of the exponent. So I have x minus 3 times log 64 equals log 16. All right? I'm trying to solve for x. I can divide by the log 64. Get him out of the way. All right? So on the left, I just have x minus 3. And on the right, I have log 16 divided by log 64. And then my final step is to add 3. So x equals log 16 divided by log 64 plus 3. You can put that into your calculator. And you will get 3.6 repeating. Yep. So if you do it using your 4 cubed to the x minus 3 equals 4 squared, you get 4 to the 3x minus 9 equals 4 squared. And then you just say 3x minus 9 equals 2. Add 9, divide by 3, you get x equals 11/3. So change your base formula says if you have a logarithm of some base of some number, right? In your calculator, you have log base 10, which is log, and you have log base e, which is ln, right? You do not have log base 4 in your calculator, all right? So the easiest way to do this is to just say log base 10 of my big number divided by log base 10 of my base. So like for this guy, in your calculator, you can literally say log 54 divided by log 4 to the nearest thousandths. So 3 decimal places. All right. The last thing we did on logs is solving something like this. Again, there's kind of 2 ways to do this. You can use change of base, or you can just do the log of both sides. And so the first thing you have to do, though, is get your base by itself. My base here is 18 because that is what is being taken to a variable, okay? I'm trying to solve for that variable. So before I do anything with logarithms, I need to get rid of that 5. 5 is multiplying, so I am going to divide both sides by 5. So I have 18 to the negative p equals 8. And we can do exactly what we did before, log of both sides. So I have the log of that left side, which means I now can get that p out of the exponent using my expansion. So I have negative p times log 18 equals log 8. Log 18 is just a number, so I can divide both sides. I would go ahead and divide by the negative as well, because there's a negative 1, so I can divide by negative log 18. And that gets rid of my log 18 and that negative in front of my p. So now I have p solved for. In your calculator, you can say log 18 divided by negative log, net log of 8 divided by negative log of 18. This also says round to the nearest 10,000th. That is 4 decimal places. So you're going to get approximately negative 0.7194. Chapter 9 was all polynomials, pretty much. So when it says simplify, it wants you to factor and reduce, all right? So I'm going to look at 28 and 16, and I'm going to say, what can I take out of both of those? I can take a 4 out. So that is going to be 4, 7p minus 4. And then in the bottom, I'm going to say, well, what can I take out of 20 and 48? I can take a 4 out. That is 5p plus 7, right? And then I'm going to see what I can cancel. In this case, all I can cancel is the 4. And so my answer here is 7p minus 4 over 5p plus 7. It also asks for excluded values. So this is the first piece, simplify. Excluded values are where the denominator equals 0. So I would look at my original, which in this case I didn't cancel a variable, so it doesn't matter, and say, where does that equal 0? And then just subtract and divide. You will get negative 7/5, by the way. 28 over 20, and then your 4 comes out, 7 over 5. Multiplication and division are the same thing. You're just factoring everything, all right? All right, so I picked the division because it's identical to multiplication. You just keep change flip, all right? So I'm going to keep the first one the way it is, 1 over n plus 5. Change it to multiplication, and then I'm going to flip this, all right? I do need to factor. So I'm going to look for factors of 36 that subtract to give me negative 5, all right? So that's n minus 9, n plus 4. That's my denominator once I move it. And then this one will now go on bottom, n plus 4. It is now multiplication. And once you have factored, you can cancel any top to any bottom. So up and down or diagonal. So in this case, my 1 will not cancel with anything. My n minus 9 will not cancel with anything. My n plus 4 will cancel. My n plus 5 will not cancel with anything. So on the top, I have 1 times n minus 9. And on the bottom, I just have n plus 5. So addition, you do not cancel top to bottom. You can reduce directly, but you can't cancel diagonally. You have to have a common denominator. You do basically cross multiplication is what you're doing. So I take the k minus 4, and I'm going to multiply it by the other denominator. And then I'm going to add and multiply that 5 by the opposite denominator. And my common denominator will be the two denominators together. 4k cubed times 5k minus 6. All right?
Too many numbers.
Don't reduce up and down. Don't reduce these 4k's. You just put them there, okay? You're going to be very tempted to cross those out, and that's completely wrong. You just put them there. Don't cancel them. So distribute on the numerator. Leave the denominator alone. You don't have to distribute him. I don't make you do that. Just distribute the numerator to simplify. So we have 4k to the fourth minus 16k cubed plus 25k minus 30. If any of those could combine, I would combine them. None of them do. If a 4 could come out of all of them, I would cancel a 4 out of all of them. It doesn't. So you really can't simplify that anymore. That one is done. Solving equations, you want to get rid of your denominators. You get rid of your denominators by multiplying by the common denominator. If I have x squared, and x, my common denominator is x squared. All right? So I'm going to multiply everything by x squared. I'm going to multiply this by x squared, this by x squared, and this by x squared. My goal is to not have any denominators. So all of your denominators should cancel, all right? Which means the first group, well, the x squareds can cancel. I have just a 3. The second group, the x squareds can cancel. I have just a 1. The last group, only one of my x's will cancel. I have 5x. That is much easier to solve than the first one, right? I have made this easier by getting rid of my denominators. So I'm going to subtract 1. This side I have a 2 and I have a 5x. Then I am going to divide by 5. X is going to equal 2/5. That is my answer. 2/5 doesn't cause any problems. I am done. All right, so you need to first remember that. Sine is opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent is opposite over adjacent. If I am asking for the tangent, I just want the fraction. Don't give me an angle. Don't give me a side length. I just want the fraction. So I'm looking for tangent, which is opposite over adjacent, all right? That is based on the angle that is labeled. So for the angle that is labeled here, opposite is here, adjacent is here. I have a little bit of a problem. I don't have the opposite side. So in this case, I must use Pythagorean theorem. In Pythagorean theorem, the most important one to place correctly is the C. The C is always your hypotenuse. So this is C, okay? Which means I can say, well, the one that I don't know plus the adjacent equals the hypotenuse. All right? And so I do need to solve for that side because I need to use him. And I'm saying this because I saw a lot of these on the test that caused some problems. So make sure that you know which side is your C. Make sure you also take the square root. All right, so now I know the opposite side. I am not done. All I've done at this point is solve for a side. I am asking you for the tangent. I need you to write out opposite over adjacent. Opposite, we figured out, is 5. Adjacent is 12. That is my tangent.